Okay, hello and welcome to my talk. I am Bohdan, and today I will present you ShieldBox, secure Middleboxes with shielded execution. It's a joint work of Technische Universität Dresden and University of Edinburgh. So let's consider Middleboxes. So typically, organizations use quite a lot of Middleboxes for routing, caching, lots of functionalities. And this imposes significant costs for deployment, maintenance, and management of such systems. So the question is whether we can outsource these Middleboxes to the cloud. So cloud has abundant and cheap computational resources and lots of bandwidth, and network function virtualizations has done quite a lot to make this technically feasible. But if you consider the trust issues and security inside cloud, you will discover that if you have a malicious cloud operator, the operator can leak secrets that are inside of your Middleboxes and learn configuration, observe the data that your Middlebox process, and so on. Also, cloud stacks are quite complex, have lots of millions and billions of lines of code, which naturally means lots of bugs, which can be exploited, as was presented earlier, and can be also used to exfiltrate secrets. So, so far, state-of-art systems have argued for direct processing of encrypted traffic, and this blind box and embark. But those systems impose a high performance overhead and offer limited functionality. So the research questions that we wanted to answer here is how do we securely outsource Middleboxes to the untrusted cloud without sacrificing performance and supporting all the necessary functionalities that we need. And for this, we designed ShieldBox. It's a Middlebox framework built with shielded execution as its main security primitive. So the design goals of our system were, first of all, we wanted to achieve high security, that is confidentiality and integrity guarantees for network function, code, and data. We wanted it to achieve high performance, that is have near native performance and ideally operate near 2-line rate. Then we wanted to have generality, that means to support a wide range of network functions, and transparency, that is we wanted to have portable, configurable, and verifiable systems with minimum changes to the existing software. So let's move on to the design. So if you consider ShieldBox not as an end-to-end system, but rather as a system that's running on a single node, you will see that the three main objectives that we want to achieve are security, performance, and usability. So for security, as I have already mentioned, we rely on Intel SGX technology, that is a shielded execution technology. And I will provide some background on Intel SGX. So Intel SGX is an extension to Intel instruction set architecture that became available in the Skylake generation, and it allows creation and management of enclaves. So enclave is an isolated piece of coded data that is encrypted in the RAM, and it is not like unencrypted in the CPU cache. And it provides the following guarantees that are hardware enforced. So first of all, enclave code running in the enclave context can read and write both trusted and untrusted memory. On the other hand, neither privileged software nor unprivileged software cannot read enclave data. And also, as far as code is concerned, enclave cannot directly call untrusted functions, untrusted code, and neither can the untrusted code call directly enclave code. There is a special entry and exit protocol basically implemented in these extensions. There are also several restrictions on the functionalities that is allowed inside enclave. So first of all, several instructions are forbidden, that is system call and read timestamp counter. And there are also high performance overhead for security memory paging. That means that the memory footstamp of the enclave needs to be kept minimal. And also there are very significant performance penalties for enclave entry and exit. Also, Intel SGX is just an extension to instruction set architecture. But if you really want to use it in your application, you need to rely on some framework, like, for example, Rust SGX framework or Intel SGX SDK. But in our work, we rely on our previous work called SCON, that is a secure container framework designed to launch unmodified POSIX application inside Intel SGX. Yep. As far as performance is concerned, we rely on DPDK to directly access network interface card. And for usability, we rely on Click modular router that provides basically elements which you can assemble into network traffic processing graph and basically use that as your middle box. There is another issue related to Intel SGX, that is that applications that use Intel SGX cannot consist fully of the trusted parts. There must be some sort of untrusted runtime that mediates the trusted part and kernel. So there are several alternatives for partitioning. First of all, we can use we can put DPDK outside of the enclave and use enclave entries and exit as a communication primitive. But in this case, we will have high performance overhead. We will require lots of re-engineering on both DPDK and click side. This will have reduce the trusted computing base of the application, which is a good thing on the other hand. Another alternative would be to partition DPDK out of the enclave and have it running on a different core and have enclave run, code inside enclave run inside on another core, for example, on a sibling hyperthread. And in this case, we will have overheads in cases when the network function that is running inside click is CPU intensive. And in this case, the core which is dedicated to DPDK would be basically wasted. But in this case, we have a reduced TCB as well. But we use a different alternative. We put both click and DPDK inside of the enclave. And in this case, we require no re-engineering. We have low performance overhead. And the TCB in this case is increased, which is an unfortunate drawback, but we accept this as a compromise. So another issue is that code that network interface card cannot deliver packets directly into the enclave because this would violate the security guarantees that SGX provides. So to overcome this, we still allocate huge page memory outside of the enclave, and deliver packets and memory buffers are allocated in this huge page memory. But still, we use basically shared memory pointer reading and writing for communication with DPDK and click. So we have implemented several additional features on top inside ShieldBox, and I will present the ones that are highlighted. So first of all, I will present the system workflow with remote attestation. So because we want to implement an end-to-end trusted system, we have to first establish trust in the platform. And for this, we rely on SCON remote attestation system. So basically, we have two roles, that is Middlebox developer and network operator. And as a first step, Middlebox developer builds ShieldBox and uploads it to some Middlebox image repository. And on the other hand, the network operator has to launch a configuration and attestation service on a trusted node. The trust can be established either via physically having control over the machine, or via running the configuration and attestation service inside Intel SGX enclave as well. And it also has to install another part of SCON remote attestation systems, that is local attestation service on the cloud node that will be running ShieldBox, after which ShieldBox can be installed from the repository. Network operator also has to configure the configuration attestation service, basically fill it with secrets and configurations, that is click program. After which ShieldBox can be launched, it will provide it will perform remote attestation, and if it is successful, the configuration will be transmitted to the ShieldBox. So we have also implemented several new elements. The most important of which is to enclave. Basically, what it does is that it copies packet data into the enclave. So the idea is that both packet data and DPDK memory buffers are allocated in the huge page memory. But for the memory buffers, we actually have to maintain a click packet descriptor, and it is created inside the enclave. But the packet data remains outside. So in the case, for example, when we have a VPN application that does ASGCM decryption of the data, it will decrypt the data in line. And in this case, we will expose the secrets in the untrusted memory. So to do this, we have to prevent this, we have two enclave elements that copies the packet data, the actual body of the packet, into the enclave. We have also implemented seal elements which encrypts packet using SGCM and unseals that does reverse operation. And the rest of the elements, additional elements, are presented in the paper. Also, we have added a Agrotech Protection. This is necessary for the following reasons. So consider how network interface cards delivers packets to the huge page memory. And we also have DPDK memory buffers pointing to this packet data inside huge page memory. So, but the attacker can forge a malicious memory buffer inside the huge page memory to point into the trusted memory of the enclave. And for each of these memory buffers, we would create a packet the click packet descriptor. And here, the following thing could happen. For example, imagine some strawman network function that selects some packets based on some pattern. And for those that match the pattern, they are processed somehow. For those that are not matched are, for example, sent back to the network. And if this happens with a malicious memory buffer, we would send the contents of the secret data inside of the trusted memory to the network. And to prevent this, we check all click packet descriptors and pointers into the mbuffs so that they do not point to the enclave memory. And in case this happens, we discard the packet. Another optimization that we have implemented is that we use on network interface card time source, because time is read quite a lot in click, for example, to do element scheduling. And if we use clock get time system call to read time, we have several problems. So one of them would be that we have to do the system call, which in case of the SCORN means that we have a synchronous system call interface, which means that we will have either reduced performance because of constantly active system call thread outside of the enclave, or we will, in case the system call thread is sleeping, we will have huge overhead due to, well, huge increase of latency for system call. If we, on the other hand, try to do read timestamp count instruction to read time, this will cause enclave exit and also loss of performance due to TLB flash. In case we use on-nick timestamp count or on-nick PTP clock, we have acceptable performance, even though it is very high. The overhead is way higher than when you do the native read timestamp counter instruction. And it should be also noted that all of these time sources are trusted, and currently with AGX, you have no functionality to have trusted time source. So let's move on to the evaluation. We wanted to answer the following questions in our evaluation. So first of all, what is throughput and latency of our system? And what is the influence of two enclave element on the performance? And there are also several other questions that we consider in the paper. So first of all, we consider the throughput of the router use case. It is basically IP router implemented based on click elements. Yeah, it's a very simple configuration. And we measure the throughput on the output of the system. We consider native click and ShieldBox. And we change packet sizes and measure throughput. And the higher throughput, the better. So evaluation result shows that we are constantly within a few % of the native version. And we achieve line rate with 512 byte packets, which is quite common packet size. We consider also latency of this use case. Here we consider native version, that is native click. Then we consider natively implemented ShieldBox without our optimizations for latency, which are presented in the paper. I don't have time to present them here. Also, we present a ShieldBox optimized version, and ShieldBox that doesn't use our optimizations, but instead relies on the NIC timer. and the lower the better. So in this case, you can see that native version has latency of around 13 microseconds for this use case. But if you move to the ShieldBox without optimizations, the latency increases dramatically for 2.5 times, and also the variance is dramatically increased. On the other hand, if we consider our version with optimizations, it totally removes this performance penalty. And also, if you don't use optimizations, but just use nick timestamp counter as a time source, you will have a slight latency increase, but it is not critical. Also, we consider the performance overhead of two-enclave element. We show it with the worst case network functions that we could use, that is as a mirror, which basically just switches the source and destination's MAC addresses in Ethernet packet. So in this case, we consider native version and native version with two-enclave element, and ShieldBox with two-enclave element, changing the packet size and measuring throughput, and the higher the better. And in this case, you can see that this additional memory copy that we do causes a big performance overhead for both native version, that is for native click, and for ShieldBox. But still, with larger packet sizes, we can achieve line rate. And with smaller packet sizes, there is a performance penalty of around 15% that just needs to be taken, because otherwise we will not have the necessary security guarantees. So this concludes my talk. So I have shown you that cloud has, on the other hand, on one hand, lots of computational resources, but we have limited trust to the platform. And now that we have trusted execution environment as a new security primitive, we can construct better Middleboxes that run in the cloud, achieving end-to-end trust. And the advances of network function frameworks have made construction of such Middleboxes practical. And to show this, we have implemented ShieldBox, which achieves high performance, high security guarantees. It is a practical system, we believe. And thank you.